Hello, we're going to do notes 14.4 for BC Calculus. Let's start off with talking about growth, specifically relative growth. The differential equation dp dt describes what relative growth is when we set that equal to some constant times p, which is what is the rate that we're talking about. P changes, the rate changes. This is based upon the formula P equals C times e to the k t. That's what we looked at yesterday. Relative growth, or exponential growth, as you called it, and we know it from pre-calc and algebra 2, is based upon this, our old PERT formula. This, though, is only appropriate for short periods of time and under ideal conditions. What happens, you can kind of think of this as, will things really in life continue to exponentially grow? Well, in real life, things happen. There are living constraints. Population growth is a great example of that. The Earth is not going to keep growing, or at least the population of humans on Earth is not going to keep growing until we reach a point where every single square inch of the Earth is covered by a human being. And then layer on top of that and that and that. It's going to reach a point where we'll reach that maximum capacity. So this, wonderful, it works, but when we talk about real life situations, we need to adjust that. What happens with relative growth, to make it more realistic, is we do something called logistic growth. What happens in logistic growth is we start here at some point and we get our exponential growth. Things start growing, 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 but then all of a sudden, due to the constraints with whatever the real life situation is, that population can't sustain this growth. And what happens is we reach this point where now we continue to grow, but not at that same rate. It starts dissipating, still growing, but at a that growth is not continuing at that initial state. What happens is we end up getting to a point here, a limit that we're going to approach here, which is called the maximum capacity, also known as the carrying capacity. Both of those mean the same thing. Okay? What can that real life situation, what capacity can that carry? Okay? This is what we're going to use the variable m to represent that. That's 100% capacity. Okay? The Petri dish cannot contain any more bacteria. We've reached our limit with the number of squirrels that can exist in that particular forest. Okay? A great example of this is what happened earlier on the year. We know that a rumor got out how wonderful and how awesome it was to be in BC Calculus, how it was the greatest course in the world. That started with 17 students. Those 17 students started telling others in Ross, and that quickly grew. Then it reached a point where, there were still some students who didn't know about this wonderful thing called BC Calculus. Those were up here. They didn't hear that it was so great and wonderful. All these down here had already heard that rumor, and they keep telling everyone because they were so excited to tell them about how wonderful this is. But then we reach this point where everybody knows. Okay? Maybe we only have 10 students left, 3 students left. There might even actually be even at the end of the third quarter, there might be one person in this school who still doesn't know how wonderful BC calculus is. So be sure to get out this afternoon and make sure that you're reaching every single person in the school to tell them how wonderful this is. Okay? And this point here is when we've reached half of that carrying capacity. That's what our y value is here. Y equals this. At some time, when we reach this, that time would be the when we have a point of inflection. Okay? When we're increasing to here, and then all of a sudden it dies off. Okay? If you look at this graph, you can see that it has a horizontal asymptote. Actually, it does have two horizontal asymptotes. They represent the carrying capacity of this. As we've stated up above. Okay? There is one, if we went back in time, that would go back in this direction. Generally, we just kind of ignore this one because we really just start our clock at some point with some type of population. But of course, we could go back to the beginning of time to some point here. But we're really interested in everything out here in this direction. So generally, we just consider it as one horizontal asymptote when we reach our carrying capacity. Here's a unique thing. If the population is above this asymptote, then in order to survive, the population actually has to decrease. Okay? If you put 1,000 fish in a pond that can only hold 500 fish, fish are going to die. That rate or the population is going to start going down. The population will eventually get to that carrying capacity of 500 fish in the pond. If we start out below with 5 or 6 fish in that pond and it can sustain 500 fish, they're going to keep multiplying and multiplying and multiplying and multiplying and multiplying until they eventually get to that carrying capacity or maximum capacity. So if our population is below the asymptote, then the population will increase. Logistics graphs, as I talked about earlier, have inflection points. Inflection points. So if y equals f of x is a logistic curve, you'll see that before the inflection point, f prime, slope of the curve, is positive. All of these slopes are positive. The population, the rate, is a positive rate. The population is increasing. Also, before the inflection point, the second derivative is positive. It's greater than 0 because we have a concave up curve point on our curve. Okay, so in this case, the population growth rate must be speeding up. The population growth rate must be speeding up. Remember when we did our velocity and acceleration comparisons, where velocity and acceleration matched each other, our speed was increasing? Well, that's the same thing here. If the rate of change of our population and the rate at which that rate of change is changing match signs, then the population growth is speeding up. After our inflection point, we still have positive slopes. All of these are positive slopes. F prime is greater than 0. But after our inflection point, we change from concave up to concave down. Our second derivative is less than 0. Therefore, the population growth rate is slowing down. But that population is still growing. Okay? We still have more fish in the pond. More people are finding out, hearing that rumor about how wonderful BC calculus is, okay? It is increasing, but it goes to a point where it's going to stop. That rate at which it's changing is getting slower and slower and slower. Which actually, one thing we should probably point out here is a nice question that AP likes to ask is, when is the population growing the fastest? When is the population growing the fastest? Well, it's always going to be at this time, whatever that inflection point is, always. Because here, you can see our rates are increasing till we get to here, and then the rate of change of the population still is a positive rate of change, but it's not changing as much as what it had been before. So, when would be at that point here. Let's talk about our logistic model and put some formulas to this. Remember, logistic growth means we've got something that happens over a long period of time. Okay? With the exponential growth, that had to be short periods of times. And we have limited resources. There's only so many students at the school that can hear that rumor. Okay? Limited resources, and it's going to take some time to get to those points. Okay? Now, I'm going to give you some differential equations here. I'm going to put them in a couple different ways because AP likes to give them to you in various forms. Well, let's start out with the initial differential equation here. dP dt is going to be similar to what we had yesterday, the relative growth, k times p, but what we want to do is get this to a point where it starts slowing down, and the way the equation results, or the result of the equation, is that it looks like this, times 1 minus p divided by m. When we look at this, k is whatever that growth rate is, kind of what we did yesterday. We found our k, that's our growth rate. P, of course, is whatever the population is at that particular time. And as we noted on the previous page, m is our maximum capacity or carrying capacity. AP uses typically carrying capacity more, but either way it means the same thing. Like I said, I'm going to give you this in different forms. From here, you could see that inside the parentheses, we could modify that a little bit by getting a common denominator. Common denominator of m would result in m minus p divided by m. Another way that this could be given to you, again, they might just give you an equation. You might have to build it from scratch, or they might give you the equation. They might give you with all the numbers looking like this. They may also factor out the m, and this could be given to you as k times p divided by m times the quantity of m minus p. And I'll show you one more way that they could give it to you, and I'll go back to the initial one. Hopefully you can see that we could distribute the k times p to both of those terms. That would result in kp times 1, and then kp times the second term would result in minus k times p squared divided by m. Okay. If you remember this one, that's usually probably your best one, but again, with a little bit of algebra, we can always work back to this one, okay, if that's what you want. Or if you see it in these forms and can remember how they look, then you can easily identify p here, k there, or m there. Okay? That's our differential equation. That's the rate at which p is changing with respect to time. we can write a formula for that population in a logistic growth model. It's going to look like this. M, our carrying capacity, divided by 1 plus our good old buddy C that we got yesterday with solving these. Remember, we got a constant. That constant's still in here. Times E to the negative KT. Okay. In this case, C is the percent increase. We can calculate that by taking the carrying capacity M minus our initial population, P sub 0, and then divide it by P sub 0. That will give us that constant C. Okay. And then what you can see here is, if we look at this, the limit as t goes to infinity, this population, as t goes to infinity, this gets really, really big, which then, of course, is going to make this 0, since that's a negative exponent. 0 times that constant will make this 0. 0 plus 1 is 1, which means our limit as t goes to infinity is indeed what we thought we'd have, the maximum or carrying capacity. Yep. So those are the formulas. You'll use these in different ways on your homework. Let's go ahead and do a few examples here. Okay. First one says the relative growth of Blairsville is 1.9%. In other words, every year that population is growing, or it's growing, I misspoke there, not every year, but it's continually growing at 1.9%. And its current population is 110,000 individuals. Write a differential equation for this population. Key word here is relative growth rate. That is not logistic growth. And this is what we did yesterday. So our differential equation is just going to be dp dt equals, this is our k value from yesterday, 0.019 times p. And this is relative growth. Be careful when you're reading these to know the difference. Okay. And then, of course, if we want to write a formula for this, they give us the initial value, which was c in our equation, which means our formula for p of t would be c, 110,000, times e to the k, 0.019 t. Sorry about that. P sub t equals initial population c, e to the k times t. Okay? Thought I'd throw that one in there just to remind you, when it comes time for the test, make sure you're knowing the difference between these. Next one is what we're doing with 14.6, our logistic growth. Start out with an easy one where they give us k, they give us m, and they give us the initial population. So we can easily just go to any one of these differential equation formulas. I'll just start with our very first one. From this we have k, we have m. We can just substitute in dp dt equals that k value of 0.02 times that whatever our population is. And in parentheses we'll have 1 minus p over 150. That's our differential equation. To find a formula for this, we need to use this formula. Okay? So P equals M, our carrying capacity or maximum capacity of 150, divided by the quantity of 1 plus, we need a C value. Remember, C comes from our carrying capacity, 150, subtract our initial population, 15, and then divide it by that same number. And this is going to give us 9. So C is 9 times e to the negative kt. Negative k will be 0.02, and then that will be just multiplied by T. We've got it. That's a formula, and that's a formula. So they could ask you some questions saying, what is the rate of change of the population when the population is 75? 75, 75, substitute, solve. They could say, what will be the population in 20 years? T equals 20. Substitute that in here, and that will give you our population, okay, based upon our initial conditions. Let's do a more realistic one. In the next example, we have a national park can support no more than 100 grizzly bears. 10 bears are presently in the park. They have done some research and found K is 0.1. They've done the work for us. We're not bothering to find the value of K since they did it for us. And our time is in years. First thing they want us to do is find the equation for our growth rate, our dp dt. We'll use the formula K, 0.01, times whatever our population is, times the quantity of 1 minus P divided by our carrying capacity of 100. There's our equation. To write a formula for P, we'll do like we did the last time. P equals M100 divided by 1 plus, again, we need to find the value of C. It's based upon M and P sub 0. C equals the 100 grizzly bears, subtract the 10 grizzly bears, and then divide by 10. And, as luck would have it, we get 9 again, but strictly a coincidence here. That's our C, and that will be times e to the k, or excuse me, negative k times t. And there's our equation, or our formula for our population. Now we can answer questions like, when will the population be 50? Or what will be the population when the time is 50 years from now? Okay? 50 years, we'd put in 50 for T. When the bear population is 50, we're substituting that in for P. Or they could be asking a rate of change problem, which we would find by finding our P or using our P in here. But this one's pretty straightforward by saying, all right, when will we get 50 bears in here? So we're substituting in for P and solving for T. That's going to look something like this. 50 equals 100 divided by 1 plus 9e to the negative 0.1 t. If we multiply both sides by this denominator and also divide both sides by, which way do I want to go here? I think that, divide that. This will be, sorry about that little brain fart, 1 plus 9 e to the negative 0.1 t would equal, divide both sides by 50, that should equal 2. Let's get rid of this 1, subtract 1 from both sides. That will give us 9 e to the negative 0.1 t equals 1, divide by 9, e to the negative 0.1 t equals 1/9. Take the natural log of both sides. I don't need to write it on this side because I'm trying to get rid of e. That's why I took the natural log of it. And the result will just be our exponent, negative 0.1 t equals the natural log of 1/9. So t is going to equal the natural log of 1/9 divided by negative 0.1, which gives us 21.972 years. And that will be our answer of when will the bear population equal 50. What's the significance of that? Well, you should recognize that 50 equals 1/2 of our carrying capacity, which means at that 21.972, time equals that, I'll call that T sub I, that's going to be that point where these 10 bears reach 50 bears, and that's our point of inflection, where now the rate of growth is not going to be increasing like it had before. Now that dp dt is going to be positive, but it's not going to be increasing at the same rate. Logistic growth, we can actually find this time here by, if you look at this, what we did over here, a shortcut to find the time of point of inflection. We can actually find that in time by taking the natural log of 1/9, the natural log of C divided by our K value. Okay. You see this 1/9, if we were to take this negative up here, can you see where this would be a negative natural log of 1/9? And of course that negative, working on this natural log, we would change this to the same calculation, the natural log of 9 divided by 0.1. 0.1 is our K value, 9 is our C value. So again, to reiterate, we can find the time when we'll reach that inflection point, when we've reached half the carrying capacity, when we are increasing at that fastest rate at that point there. Okay? Now, next one, we've got a fish population. It's in thousands, so be careful when you're answering to look for that type of stuff. We've got a man-made pond, and they give us this equation here. They ask us to find K and M. If I want, I could factor this out, factor out the 0.8p. This would be 0.8p times 1, factored it out, minus, well, if I factor out a p, I won't have a p, but a p squared, I'll have just a p. And then if I take and divide 0.1 divided by 0.8, wouldn't that be the same thing as writing it as p over 8? This is of the form that we show here, but by factoring it, I get it in the form that we've used the last few times, the very first one, K times P times the quantity of 1 minus P over M. Easily to find K, easy to find M. K, of course, is going to be equal to 0.8, that guy right there, and M is going to be equal to 8. Okay? And remember, 8 represents not 8 fish, but 8,000 fish. Now, this equation, if you put that in your little slope field equation, or program, it would come up with this slope field, which helps us when it asks this question. Suppose the lake is initially stocked with 1,000 fish. Sketch the solution to the curve given their slope field. We would start here at B at 1,000. Remember, this is in thousands of fish, so 1 would represent 1,000. And then as we go, again, remember, we're going with the flow. We're not jumping and connecting any dots here. You can see the flow is going to want to push us up in this direction. And as we get up here, all of a sudden we reach a point where now it's saying, okay, Don't get so excited here. Slow down, and we go to here. And that would be B's. Don't want to go over that. Suppose the lake is initially stocked with 11,000 fish. In that case, we're going to start up here at 11. 11 represents 11,000. And this time, it's taking us down. When we go with the flow, we're going to look something like this. And this represents the two ideas we talked on the previous page, is if we start with too many fish in here, they're going to die until they reach the point where they have the carrying capacity. There's not enough oxygen in the water. There's not enough food in the water. Okay, so whatever the restraints are, they cause those fish to die off until we reach our carrying capacity. Here we have plenty of food, plenty of oxygen, plenty of nutrition, plenty of room to swim around. They keep growing and growing and growing until now we reach this point. Okay? From our differential equation now, let's show that the rate of increase of the fish is greatest when there are 4,000 fish. Okay? Greatest, that's implying that we want to look for a maximum. We want to find dp dt's max, the rate of increases max. When will that occur? Well, that'll occur when, what? The derivative of that equals 0 or does not exist, and has to do a sign change. Must change specifically from positive to negative. Okay? So let's look for dt's derivative when that equals 0. If we go back to our initial equation, it's kind of nice to have it in this form because we can just take the derivative of that. First term is going to be 0.08. Second term will be minus 0.02 p. Just took the derivative, those easy derivatives. And now what we want to do is check when this second derivative equals 0 or when it does not exist. Does not exist, pretty simple there, no issues with that. But when we set this equal to 0, subtract 0.8 from both sides, divide by negative 0.2, p equals 4. At p equals 4, we're going to check our second derivative. On this side, we're going to get what? Positive value. Okay. When we are less than 4, such as 0, if we want to put that in there, when p equals 0, we're going to get a positive value over here. On the other side, we're going to get negative. This is a positive, negative type situation here. So we've got a 0 here, and we do change signs. Therefore, p equals 4 is a maximum. Therefore, also we can conclude that, therefore, the rate of change is maximum at p equals 4 or 4,000 fish, since p equals 4 represents 4,000 fish. Next thing what they ask us to do is evaluate the limit as t goes to infinity. The limit of that, we don't have to go back and write an equation for p and evaluate that. We can get that from our slope field. Hopefully you can see from our slope field that no matter where we start, we're always going to this carrying capacity of 8, or 8,000 fish. Okay. So we just did some basic examples of these. Remember again on your homework, You might be given these values, you might be given the information in a real-life scenario form, or they may come right out and give you the equation. Regardless of how they give it to you, refer back to these equations, and you should be doing great on this work. That concludes the notes. Please enjoy the homework and also enjoy your spring break.